Cool. We can look at that actually. So basically, in homework you want to figure out what these are. But as you can see, we do have a slide for that. But we can sort of like go over that, you can basically just look at these figures to try to figure out what the output size would be. So this is the default way to do it, which is padding equal valid. So we are actually using padding equal sum here. So basically, when you slide over stuff, you will pad the size into something that you will output with the same shape. So whenever you see padding equals same, basically that means your output will be the same shape. So if you look at this, that basically means that once you go through this layers, the shape won't change. So the input will be 164, 64. So after going through this convolutional layer, it will still be 64 by 64. But now you have like a channel. So after this, you will get a 64, 64. And then ReLU doesn't change anything. And then you have the pool layer. So you sort of like have the size. So there's this calculation, but basically if you're using padding equals same, then everything will be the same. And stuff would be a bit complex when you have like striding, but in our case, we are not using striding in our convolutional layer. But when we are doing, if you are doing striding, then your size will be smaller after the convolution. So in this case, if you have stride 2, usually it means that your size will be, half. And then if you have stride equal 3, then your size will sort of like become 1/3.
What's the striding? So you're just skipping calculations, right?
Yeah, exactly. So striding, for now, you won't see a big difference, but think about striding is used intensively in wavenet. So when you are using waveform and then you want to sort of like, you have like 441 kHz pitch. And if you try to do the CNN waveform, if you do without stride, then 441K 4.1K, and then the next step will still be 4.1K. So striding is a way to sort of like do downsampling on the way.
So like each this process striding is be like continuous data, like you can skip some of the intermediate.
It's just jumping. So
Like
technically,
because like you don't gain much more information by doing every consecutive value.
exactly, yeah. That's the point. So striding, it seems like a magic, but if you have overlapping information, pretty much you're good enough. So people will try something like, the first layer you do striding equal 3, the second layer do striding equal 5, and the next layer do striding equal 7. So 3, 5, 7, those are primes, and then they can sort of like combine and cover everything. So that's one way to do it, but the other way is just do striding equal 2. That's sort of like combine, downsampling to a factor of 2 plus convolution at the same time. So striding is actually used in the other side in what we call transport convolution or deconvolution is when you want to grow the size, you will see the effect of striding more. But yeah, basically striding is just a different way of doing downsampling. But traditionally we don't do downsampling on the convolutional layer, but we do downsampling in the max Boolean layer. So max Boolean layer, in our example, we are using this Boolean layer. Note that Boolean layer doesn't have any weight, so we reuse it over time. It's the same Boolean layer, same dropout layer, same dropout 2D layer. So these are, there's no weight. So once you initialize it, it's just, some max function. So here we are actually doing 2-2 striding. So that actually means that we are using the 2-2 filter, and then we jump, That's right. Actually, the first parameter is the size. So it means that it's 2 by 2. And the second one is the stride. So it jumps for 2. So that's the max Boolean layer here. That's sort of like the default way how people do it. We don't do overlapping in max Boolean layer. So you have like 2 by 2 filter to get the max Boolean, and then you jump 2 pixels at the time to get the output. So, in our case, this is the simplest way that I usually do my CNNs because that's easier for you to calculate. So basically, convolutional layer, we do whatever shape using stride equal 1, and we do padding equal same. So output doesn't change the size. So, if it's 64 by 64, it will still be 64 by 64. And the max Boolean layer will downsample it half. So this make it very easy for you to compute the size of the CNN. So basically, over the time, it would just, be the same if the convolutional layer doesn't change with ReLU or pooling layer, and then dropout will shrink it. Nope, not dropout. The pooling layer will shrink it by half. That's why you go from 64 by 64 to 32 by 32, and your channel become the first output layer of 8 channels. So, Q11 would just be, half the size again, because you have the pooling layer, and, the channels will go up to 16, and so forth, so on. So you can sort of like guess what those are. Just keep halving the size of the image, sort of, or the spectrogram, and then you double the filter over time. Is that clear? But in practice, if you have like weird striding or weird, or you're using padding equal value, that's the formula that you have to use. And sometimes you will go from 64 by 64 and jump to, I don't know, so something like 59 by 59, and things become trickier because you will get weird shape. So usually what I did is just using padding equal same so that the output is the same size. So 64 by 64, still 64 by 64, power of 2, easier to tackle with. And then I do, max Boolean to half it. So again, it will be 32 by 32. So always power of 2. That's much easier to handle. That's sort of the reason why I like this architecture. And pretty much different architecture will work pretty much similarly. So don't worry too much about the exact architecture. Cool. So we have this in our slides. So it's just similar to the case. So again, this is like input channels, output channels, kernel size, which is the filter size, the pattern detector that you have in your convolutional neural network. So your input will be one channel. So spectrogram is just one channel by 64 by 64. The second layer would be, output will be 16 channels. So you learn 16 different sort of like detectors, and the output will be 16 different activation for those 16 detectors that you learn. But the output size will be half. And then you move on, your pattern detectors, number of that will keep increasing, but your image size will shrink. So that's pretty much what Q1 is about. Cool. Any other questions? Yeah.
No, go back to the slide. This is like a dumb question, I think, but like, how are those two,
This? Nope.
and are they classes or functions, I guess? How are those two chunks of code related?
Oh, you mean these two?
Yes.
So this is the class. So init means that you are initializing these stuff.
Okay.
So these are creating a layer. The reason why we need to create a layer because these layer contain some weights that you need to learn. So basically this initialize 16 3x3 detecting. And then, doing the forward function is how you define, how you use those detector to do your stuff. So the first time you initialize this will sort of like randomly initialize all the detectors. So the 3x3 detectors, there will be 16 of it inside this. And then there will be 16 by 32 combination of weights that you need to learn. That's, kernel size of 3. So basically these 4 lines initialize a bunch of, pattern detectors under the hood. And this is how you use them. And you will train it so that these, pattern detectors become better and better.
And you kind of were talking about it like being like a consecutive kind of way. So is that like, is it doing them in an order, I guess? Like is it doing them one after the other? Is it doing?
So these are sort of like parallel, these are just saying that, well, we have these, detectors, we have these detectors, but here is that, the input will be X and we want to define what the output is. So usually it should be, return Y, but here we are basically just doing this function again and again. So, it's sort of like, to break it down, it will be, our input will be X, and then we do X equal cell count 1 X. And then we just, so the new X now will be after the convolutional layer.
Yeah.
And then you just do, brand new X, and then you just do Boolean layer X. So you just do a bunch of that, but this is just like one layers of it. So, this line just go through convolutional layer, go through ReLU, go through pool, and then you get sort of like first layer of it. And then you put this X again to the next layer, and then you go through again and again. Okay. So in the end, you will go through all the layers. So go through convolutional 1, ReLU, pool, convolutional 2, ReLU tool, blah, 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 and then flatten, and then go to fully connected layer, last layer.
All right, thank you.
Yeah. So yeah, it could be a bit confusing at first, but yeah, but and there's a lot of things going on in these lines. It create those parameters, it register into this NND module. So there's a lot of things going under the hood, and when you code the optimizer, it sort of knows that some of the parameters is being trained, some of them are not being trained. So when you are inherent this NN module, it will handle everything for you. So that's sort of the beauty of PyTorch, but also the complexity of PyTorch. A lot of things is actually happening under the hood. That what you see here is a very high level interface. Cool. Let's see.
But can you go to animation forward? So I printed out the size and like after all of those, and
there will be a batch.
Yeah. So
size. It is fine. Yeah.
What?
I mean, there will be a batch axis in the front. So that's fine. You usually get 32, 16, 32, 32, 32, 32, 16, 16. So you will get a batch size in the front. You should get 4, right? 4 number.
I got. Oh yeah, I got 4 numbers at the beginning.
Yeah. So that's the complexity. So this is like one single image, but when you train the model, you actually have batch size. So when you print it, it should be 32.
Yeah, 32 each time, right?
Yeah. So the input will be this. But either way is fine. So and blah blah. So the first channel would be the batch size, which is another tricky complexity here. So this is the batch size. So batch size pretty much means that it's not just sending one single spectrogram into it. We are sending 32 these things into each of the training loop, because we were talking about that mini batch stochastic gradient descent thing, that we don't want just one single image and then spectrogram, and when we optimize for it, it's too noisy, but we don't want to compute the whole million of samples and compute like a batch like a gradient. So we sort of like choose some numbers, so 32, 64, 16, or 128. So you grab a bunch of spectrograms, try to figure out what's the optimal way to do better on these 32 samples. And then we go for the other 32 samples. So you go through different samples. That's the whole training loop is doing. So, you have like, say, millions of spectrograms. You go through 32 as a batch, and then you go through multiple batch in each epoch.
How does I print out the size between, and my numbers just don't line up with what's on there. That's why I was confused.
Oh yeah, that's different. I mean, so
it's not the same one.
yeah, it's not the same one.
Okay.
I mean, it will be too easy if it's the same one. Yeah, so
I
there's still
don't-
some, there's still some complexity. Here we have 8. So 8, 16, 16, 32. So, you guess this will be 8, this will be 16. That's pretty much it. But I mean, the idea is that they are slightly off, but basically the same stuff.
Is the batch made up of like copies of the same image?
Different. So different spectrograms. So yeah, so pretty much you say you have like millions of images, and then you just grab 32 of them, and then you go through different batches of 32 different images. And that's being handled by the dataset thing. So in PyTorch, even though we are just shift entering all the time mostly, but this is how PyTorch handle data set. So this basically initialize that. So my whatever data set that I'm defining is actually a child inherent by to the torch.utils utilities.data set. But basically, these again is just defining what files you need. But look at the get item thing is the key, so that it will define how you get the specific item. And the length will give you the length of the whole data set. So the data set would be, when we are doing the initialization, we just basically load the metadata, and then we load all the file names. And then we go through all the file names, we load all the cell, the mail spectrogram. So we do np.load file name, and then we append it to the self.mail specs. So this is a new list. So we will have a bunch of mail spectrogram, and we have a bunch of labels. And at each time when you query, say, I want the 10th sample of your data set, it will just return whatever being stored in that. So think about this as a, sort of like a library that has index by some number. So you have a bunch of spectrogram plus this label stored in this sort of library thing. Once it's done, you will sort of like create your spectrogram, and you will wait a bit for it to load. But the complexity of data loader comes from that line where we have the batch size. So once you have batch size 32, now this thing is the data set that we just talked about. So the data set is a library that sort of like, or dictionary that defines how whenever you give that a number, it will return a specific sample from your data set. So this will create a data loader on top of that thing. You have a dictionary that knows, sample 1, we have this spectrogram plus this label. Sample 2, we have this spectrogram plus that sample, blah, 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 until, millions of spectrograms and label pair. So this will sort of like go through that data set and create 32 spectrogram plus labels as a batch. and you will shuffle stuff around it. So this is sort of like think about it like a, I don't know, like an Amazon worker-ish. So it will be in the warehouse, go into this shelves, and then collect 32 of them, and then package it into one package and send to the GPU so that people can work on it. So think about it like a factory. In PyTorch is that you have this as your shelf, you have all the stuff on shelf, and then the data loader will be some worker that's working there so that grab stuff, grab 32 of that, and then compile them into a package and then send it to GPU to train. So when you are going through the data set, you are actually going through this training loader. So basically you are running this for spectrogram labels in enumerate stuff, but basically what you're doing is looping through this training loader, and each of the package out from the loader is 32 spectrogram plus labels. Cool. Yeah, but I mean, there's still a lot more. I mean, a lot of stuff, optimizer quite clear around. Won't go through everything, all the details, and this is the magic where backprop the gradients. So this is the actual magic of the whole machine learning training. Everything else we just talk about is how you get something out from the model. But the biggest the key of deep learning is that you have to train the model. So this is exactly where you do it. You backprop, and then you update the weight by optimizing the optimizer. So, the key of deep learning is here, that you have to do a bunch of stuff so that to enable this. And it will happen automatically that go through the backpropagation because you define everything in PyTorch, so that PyTorch will handle it for you. Kind of like laggy. Cool. Questions? I mean, we should just go over it, and if you have questions, we could go over it. The key is not to, the key is to give you all the answers, sort of. Just do minimum stuff. But if you want to explore different, different architecture, different optimizers, stuff like that, go ahead, try it. I mean, there's no requirement. You can train your own model, and pretty much everything else doesn't has to be the exact model that I'm training. So if you get something that's totally different from this, it's fine. I mean, there's no answer, golden answer for these. So feel free to explore different stuff, and it's a Jupyter notebook. So the point is that whenever you are in doubt what these are, just print shape, print extra shape, or you can even just do whatever stuff to print anything that you're interested in. But everything else should be just doing shift enter all the way once you train the model. Cool. Let me see. Cool. So homework 3 due today. Is that fine? We need to extend it. I'm fine either way. So if you want more time, just let me know. We could extend it to Wednesday or Friday. It's fine for me. Or let's say we just extend it to Wednesday, I guess. Because there's still some complexity, as you will see. Cool. So last week we were talking about CNNs. So the key idea of CNNs is to learn this reusable pattern detectors. So that's the high level intuition that you want to remember, that CNNs except that it just looked complex. You know, to be honest, it's one of the easier neural network that you can understand. So that's why we started with CNNs. You know, over the time you will see, RNNs, transformers, blah, blah, blah. And those are, well, cool. Most of the time you won't even see a real reason why they work. But anyway, CNN is sort of the idea of reusing pattern detectors, and we are learning those pattern detectors. So, we go through a bunch of convolutional layer, pooling layers so that, one thing is you slice through your detectors to detect different stuff, and then you use pooling layer to sort of like reduce the size so that it become more, high level aggregating information that you learn from the image. So, once you detect the beak, you don't necessarily need to know where exactly the beak is. You just need to know, well, there's a beak somewhere over there. And whenever you see a beak and then this, penguin shape, and then you see certain, relatively occurring features of a thing, then you sort of like know that it is a penguin. So that's sort of the idea of CNS. So over the time, you grab higher level features from your input image, and at the same time, you reduce the spatial resolution so that you sort of like just know that, well, there's a face here, there's some circular stuff here, there's some, grid-like structure here, and then how does that compose into this thing that you are interested in? So after doing that, usually we just flatten it into a single long factor, and then we would just do a bunch more, fully connected layers. So in our case, we are using a very, very simple CNNs that, go through 3 pairs of convolutional layer plus pooling layer. So, sort of like make it 1/8 the size of the input, and we are using much fewer filters in general. So we are using A16 and 32, but usually typical how I would start is like 32, 64, 128. So, we are using a very, very small model in our case so that it could run fast, and, feel free to double the feature size to see whether it improves. But after that, we will have several dense layer, which is the linear layer that we talked about previously. That's the, simplest deep learning. That's the neuron that's connected. But in our case, there's just one dense layer. Cool. So convolution layer, the goal is to learn a bunch of, reusable kernels or filters that detect different patterns. So this would detect that slope. And, last week, we sort of like talk about how you can combine these low level things to, potentially in the next layer form a circle detector by combining different slope detector at the same time. So benefits of CNNs, local patterns, invariant to shifts, reuse that learned filters. And this is important that it's reusing across different parts of the image, but at the same time across different images. And it's much more parameter efficient. So as you can see here, the input in our case would be sort of like scale image, or, we have that color, but it's basically just one channel, and the channels will increase as we go deeper. So channels, sometimes you see feature, sometimes you see channels, sometimes you see number of filters, number of kernels, they all mean the same thing. That basically means that how many different, patterns you are looking in during your convolutional layer. So, you will have like 4 different pattern detectors, say, different slope. Maybe the next layer you will have beak detector, fur detector, wing detector, or, feet detector, eyes detector. So you will have a different detectors over time. You will have more and more detectors because you go more high level, it becomes more complex. For example, we just go through this. And we look at, learn CNN kernels and the top activation. So these are some of the CNN kernels. So you can look at it. You see that boundary detector, you see color detector that, sort of like detecting different stuff in your images. So top activation is that, look at the whole data set. You just scan through the whole data set using this detector. So, in this image, you scan through everything, and in the next image, scan through everything again, and look at your data set. What are those having the biggest activation? What are the thing that's being triggered by these detector? So, when you go deeper into layer 2, you see that there are more structures into it. So circle detector, we talk about, you can use sort of like 8 slope detector at different position to sort of like mimic the circle detector. But you can also imagine that you can use 2 different, horizontal edge detector and vertical edge detector to create a corner detector in the second layer. And that will also triggers some of, be triggered by some of the patterns in your real data set. And over time, you will see that it become much more complex, grid detector, now you see human detector. And even later in the stage, I think this is layer 4, somehow there's no layer 3. So this is layer 4. You see dog face. So you also see this activation in the trend AlexNet. So last time we are guessing what these are. So if you increase the brightness and contrast, now you see that this, owl-like, but it's actually a cat here. But anyway, you can see that these different detectors, when you increase the brightness and contrast, you can see that it's actually detecting different stuff. So this will be detecting the right edges. So this will be detecting the left edges. So different stuff, detecting different things. And this will be sort of like detecting the background. And this will be detecting the brightness generally. And in deeper into the convolutional layer, you see that it doesn't has the shape of, no longer has the shape of the cat. So now it's more like, detecting something high level. So, there's a bunch of stuff in the middle. So it's sort of like detecting maybe the cat face. But, some of that will be detecting maybe this, like the cat is standing in a grass, then this could be grass detector. So it depends on what you're detecting, but over the time, deeper into the model, it will detect in something more complex, and you no longer see the low-level structure. Cool. Still questions on CNNs? Oh, good. So the idea is that we are learning some detectors to detect different stuff. That's the key of CNNs. And in our homework, we applied it to do spectrogram classification. We are doing instrument classification on spectrograms. Cool. So today we'll be talking about music classification, but just to recap that now we are going into different applications of the thing we just talked about. It's just like deep learning 101 in 3 lectures or 4 lectures. So it's a lot more than that. If you want to learn about deep learning, there's a lot of different courses, but the course this course is not about deep learning. But deep learning is just a way to give you the flavor of, more than AI music systems, because lots of them are actually based on deep learning. But, I guess this will be the most deep learning homework for the whole quarter. The next homework will be just, grabbing some, pre-trained models and just run it. And, pretty much you won't see anything under the hood. But that's sort of the way how you use these models. But it's also good to know what's actually being trained or being used under the hood. So we would talk about, analysis, our creation and retrieval. That's pretty much the 3 main thing about music information research. So we will start with the analysis. So, in our homework, it's basically doing note instrument identification or instrument recognition. So that's sort of one way to start with the analysis. So today we will talk about music classification. So classification will be the simplest form that, AI can be used in music. So, you can just classify a bunch of different things. Whatever you can figure out how to get data set from, you can basically train something to do it. Your model will work to some extent if it makes sense. So, you can do genre classification, pop rock, R&B, jazz, hip hop, classical, blah, 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 different genre. You can also do mood classification if it makes sense in some sense. If you just want to get high level features, sad, happy, sad, calm, aggressive, cheerful, then potentially you can do mood classification this way. In practice, we seldom do mood classification directly in this way. We usually do it continuously. So there's another way to model mood as regression problem. So regression is predicting continuous values, and classification is predicting discrete values. But anyway, if you formulate your model, your task as classification, you can still do mood classification. And you can do instrument recognition, basically what we've done in homework 3. But think about more broadly into if you listen to a song, it's like 3 minutes. You could just see whether there's this specific instrument, is guitar in this composition, or is oboe in this composition. But you can think about even harder than that, can we sort of like detect how the instrumentation goes over time? So you do sort of like temporally instrument recognition.
Do classification a lot, but if you work, like if you had to, would that be something you would have to, like the data set itself that you're analyzing, like you'd have to have like each song would have to be tagged with a label of reclassification, or like is there a way to use
without labels?
Like if you didn't know the labels, I don't know. To still class, like would a mouse spectrogram or anything?
Yeah, I mean,
invest that.
So most classification tasks is, you have to have labels in the end. Think about, some unsupervised way to do it, nearest neighbor or k-mean clustering. At the end, you just get a bunch of different clusters, and you still need to know what this clusters is. So think about animal or instrument classification. At the end, you get a bunch of stuff. They are the same groups, but you still don't know whether these are the guitar sounds, these are the bass sounds. So I would say at the end of the day, you still need tiny amount of labels so that you know what those are. But the easiest way to do it is through supervised learning, just having data set with all the labels. But people also do weekly supervised learning. So one way to think about it, it's sort of like if you have 90% of your data without labels, can you learn something from that by just reconstructing itself? That's the typical way of doing it. But can you create some tasks that just learn something about music in that 90% of unsupervised stuff, and then use the 10% label portion of the data set to understand what classification is about. So that's called semi-supervised learning. There's so many different ways to do semi-supervised learning. And to be honest, that's actually the way how people do it in real life. But usually, most of the time, we will start from supervised learning, that assuming we have a bunch of labels. But there are ways to do it with only knowing partial labels of your data set. Yep. Cool. And we also have like composer identification. Think about it. Say, if it's Mozart, it's Bach, it's Beethoven, maybe a bit easier to understand. But now if you are think about pop songs, if you have singing voice, it's much easier to see if it's Taylor Swift or Bruno Mars. But if it's just the background music or think about instrumental music, then it could become much trickier in this case. And you have key detection, chord estimation, that's more fundamental, just trying to see what the key is, what the chord is. And pretty much you can combine everything here into music tagging. So music tagging is just, can we just, that's how we do it in YouTube or whatever. Lots of different on live volume is that you upload something and then you just tag it, say, this is pop. I think this somehow jazz and somehow sad and, aggressive at the same time. So you will have a bunch of different stuff. And maybe you also have a tag for, it's a cello plus violin-ish thing, and maybe tag for composers. So music tagging is just like a catch-all thing that, you have everything as tags and you sort of want to do music tagging at the same time. So these are all music classification tasks, and most of the time it depends on what data set you have. There are some existing public data set, but to be honest, if you want to do real stuff, you will have to have access to, bigger music catalog or corpus. Cool. So why should we care? So some of the application of music classification models includes, recommendation. Think about how, YouTube Music or, YouTube Music, Spotify, Apple Music, Amazon Music, how they knows what to recommend to you the next song, what to play next. Most of the time, because, music, when you listen streaming, it's like 3 to 5 minutes. It has to just recommend you again and again over the time. It's unlike, movie recommendation. Movie recommendation is that you spend a lot of time, figure out what to watch, and then you spend the rest watching that movie. But for music recommendation, it's sort of like keep doing that again and again in the next few hours. It could also be applied to curation. So think about potentially you are Spotify and you want to see, different type of music that you want to potentially get more of that music from, or, look at your database to see what kind of music that you want to learn more about. So it's also applied more than, just music streaming service companies, but think about libraries, think about our school music library. Can they look into all the songs that have in their digital library and see what type of data they have and what different eras or different specific genres that they should curate. It could also be applied to playlist generation, to generate a playlist so that you can play in your streaming service, and listening behavior analysis. We'll see some example later. And it can also be applied to musicology research. This is a very interesting to do musicology. So musicology traditionally is that you've been looking to see whether there's some hidden trends in how music evolve over time. But you can also look at a data-driven way to see that does certain genre actually being influenced by another genre, or does we looked at that weeks ago that the overall pitch, the singing voice pitch increase become higher and higher over time. So that's some sort of like musicology research could be like. But if you look into composer or genre classification, you can see how genre flow over time or evolves over time. So that could be a different way to be applied to different stuff. So music classification for recommendation. Guess which is the most popular. I think that's too obvious. Have you heard of Pandora? Oh, cool, cool. Oh, so is that the, I don't know, generation gap?
Yeah.
Okay, interesting. I don't know. I mean, cool, cool. Ah, okay, yeah. I actually visited Pandora headquarters last semester, and I was like always wondering what are actually using Pandora because they have a large number of users. I was like, well, Auckland, it's just across San Francisco. It's Auckland, which is Bay Area.
Like Berkeley area. Oh,
Berkeley, yeah.
Oh, okay.
Yeah.
Kindle was like,
Yeah, not the Auckland here. Yeah, in Bay Area. Yeah. They're quite active in misinformation retrieval. So well, guess we do have a bunch of folks. So this is the actual survey. So Pandora is not too bad. Yeah. It's 23%.
I also don't believe that. I don't like who is
Amazon.
using Amazon?
So
well, what if they just take people who
Study
subscribe
my
Prime? If you get it for free,
Yeah. I think so.
yeah, I think Amazon, I think they include Prime Music.
Oh,
So
okay.
maybe that's why. Yeah, because you get. I actually try Amazon Music once because like including with Prime, and I think student get like unlimited high definitions for $1 something. So I tried it, but I mean the search algorithm doesn't work that well. And as you try this recommendation thing, you will definitely realize the biggest challenge of these algorithm is that when you start, they have no idea what you like. So that's the biggest issue in recommendation. But we will look at that later. In the class, we would talk about recommendation and talk about retrieval. But for now, how this classification for a recommendation. So you have a bunch of songs. Likely, to be honest, you will have the labels when you upload the song, or when the think about the companies collecting these buying copyrights from different artists, then they will sort of have some labels when they put it into their database. But think about potentially as community-based forum. So think about, I mean, SoundCloud, think about YouTube. Sometimes if it's not YouTube music, if just YouTube videos, sometimes people won't upload any description or text for that. So can the system somehow guess what the genre is, so that you can do better on what to play next. So this is sort of like how recommendation can play into effects into music class recommendation system. So pretty much recommendation in different form, but the biggest question is what to play next. And in different forms. So one way to think about it is playlist generation. So pretty much that's what's being done. Play next several times. That's playlist. So it could also be applied to playlist generation. So you have a bunch of different genres. So you can potentially say you want to soul playlist or plus R&B playlist, then you can just grab them. But if you want rock, you can grab them. So this is like a more traditional way of doing it. Nowadays things become more interesting. So now YouTube Music have this Ask Music thing that you can sort of like ChatGPT, and you can ask for whatever things you like. You can put something like, well, I'm not feeling great right now, play something that cheers me up, something like that. You can talk with it, and it will generate some playlists to sort of like do it for you. And similar features. So there's the text prompt, so sort of like a ChatGPT-ish style. And it also being used in Spotify. So actually Spotify is earlier than YouTube Music. I wanted to swap the order, but I forgot. But anyway, Spotify also have a similar feature that's AI playlist, so that it's still on the beta. I think last August they wrote it out. Well, it's April 2024. But anyway, you can do things like that. And in addition to AI playlists, so think about more from the listener side. We can also do, well, it's not from the listener side, but both listener side and also the streaming service company side. Can we model the listening behavior or different users. So, if you've used YouTube Music, at the end of the year, usually you will see something like a yearly recap, and it will give you some, words that characterize what your listening behavior is like. And so that needs to do some classification on the songs that you listen to and to sort of like summarize what you like. And, Spotify also has this listening personality stuff in 2022. It's no longer available, I believe, but, they'll also sort of like understand what your listening behavior like. And to do that, they have to sort of like know what genre you listen to, what, artists you listen to, and see how you behave differently on the higher level rather than per song recommendation. Cool. So, in terms of how you approach classification, it's very straightforward, I would say. Pretty much it's binary classification, multi-class classification, and multi-label classification. So you can sort of like guess what it means by just staring at them. So, most of the time is that thinking about how you want to formulate your problem. Is it, just binary classification? It's just like, is it a cat or not? Or multi-class classification like we do in homework, that you have multiple class, but it could only belongs to one class. And multi-label classification is sort of like tagging, that, you have different tags and you want to know what tags correspond to this particular example. So to start with, binary classification, the easiest one, you have some song, you go through some, model or neural network, whatever. The output is say, well, is it classical or not? So remember that we sort of like mentioned something about it, is that, this is how we do, how we turn some numbers that's output by the neural network. So, I mean, you can use other models to do it, but, in the deep learning idea is that you have some model that outputs some numbers, and then you will go through that sigmoid function to turn it into something in between 0 and 1. So the more positive it is, so X will be the number. So 2.1 will be somewhere here. So if you look at it, it's already 0.89. So, the more positive it is, it will be closer to 1, and the negative side will be closer to 0. So, you could grab a bunch of different audio, and you get, 4.86, then you get something even closer to 1. If it's a negative number, negative 1.87, then you get somewhere here, So you get 0.13. And then, minus 3.52, that will be closer to 0. So 0.03, and then you get 0.54 for, 0.18 in the row output of your, neural network. So this is what the sigmoid function is about. And, we talk about how we can train this model by using binary class entropy to train on these, whether they make sense or not. But anyway, assuming that we have this model already, that, it correctly predict these stuff. So the idea is that how can we turn these numbers into whether it's classical or not? Any clue? Any clue? Just do thresholding. What's the threshold should be like with these numbers?
Just like assign the value to like the value of classical things and whichever number is closest to that.
Yeah, but there's the obvious numbers here, 0.5. So basically, what sigmoid is doing is actually a soft thresholding. So you can actually set different thresholds. So this could be also be determined by the validation set. You can go through your validation set, figure out what the threshold is, but you can also just grab 0.5 if you don't want to find the perfect threshold. Then 0.5 would be something you start with, and then you can think about how you can do better than that. So, sigmoid again is a soft thresholding. You don't necessarily know where the threshold is. But you can choose 0.5, but the best way to do it is to go through your validation set to figure out what the perfect number is. Cool. So, if you just use 0.5 or whatever threshold, then you can just do your binary classification by applying that threshold to your numbers that you get. Cool. So multi-class classification. So this is basically what you did in homework 3, or what you have been doing in homework 3, that you are just trying to guess what the specific class out of a number of different classes from. So the only rule is that you can only predict one at a time. So in this case, if it's an organ sounds, then you get the organ lights up that what you want to get. So in our example, we have this something like this at the end. If you train your model, so this is the one that we have in the example code. So once you train this model, it will output something that sums to 1 because you do the softmax at the end. So, this is sort of like 0.05, 0.05. This is sort of like 0.9. So they sort of like sum to 1. And you can see that, flute sometimes could be, misclassified, sort of like could part of like string and vocal and reed. So, sort of makes sense because they sort of have that, potentially confusing timbres. We'll see something later. So once you get that, just grab the highest activation or highest probability one. That's your output. So something more complex is multi-label classification. So think about it, you have a bunch of different, songs. I just use album as example. So you can also do album genre classification. It could be much more complex than song level classification. So, think about it like this way, that you want to potentially have different tags. I just pick whatever Wikipedia says, or, whatever YouTube Music says. But sometimes it can be confusing, but suppose that these are the labels that we want to get. So sometimes it's like soundtrack plus classical rather than just soundtrack or just classical. It's both. Or, it's alternative, but alternative also part of rock. And, sometimes it's a mix, soul, R&B, and pop. So the way how we do it is that, we want to have this model that have some audio input, and the output would be a bunch of different texts. And, it doesn't has to be just genre. It could also be emotion, say happy, sad, cheerful, aggressive, blah, blah, blah. It could also be, maybe the ensembles, the instruments or different stuff of it. And, like instrumentation, say symphony, or is ensemble, or is a string quartet, sort of something like that. So the way how we do multi-label classification is actually usually through 2 ways. So we can first turn it into a bunch of binary classification. It sounds funny, but this is the most popular way to do multi-label classification. So the idea is that, you get some audio, and then you just train a bunch of model, and potentially usually these models are shared. So it's the same model, just that you have different hats at this final layer that point to different classification hat. So, is it classical? Is it soul? Is pop? Is rock? Is R&B? So you have like different labels that you're interested in. And, then you do the binary classification on each single tag, so that you get the tagging. And there's a bunch more to be discussed, how you actually set the threshold for each single tag. But at the same time, are there, now you are doing independent classification over different tags. Does tags has interdependency? That's something you also need to look into. Sometimes there are hierarchical tagging system that, you have rock. Then now what rock is that? Is it alternative? Is, indie rock? It's a, what other rock do we have? funk, or is funk part of rock? No. Well, I'm being very controversial, but yeah, so hierarchical classification could be a thing. So I don't know what better, what better example do I have? Oh, maybe pop, you can just do C-pop, K-pop, J-pop. That would be, subgenre within pop. But debate what genre classification could be. Anyway, that's the first way to do it. The other way is through multi-class classification. Things a bit like strange, but this could be a way to do it. Usually less common than the previous one. You can just do power set of all the genre that you have. So say you have pop, R&B, soul, classical. Then you do, pop, R&B, pop, soul, pop, classical, or you do 3 of them, blah, 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 and you do 4 of them. So, you can basically get 2 to the power of 4 minus 1 combination of all different label combinations. So that could be the way to do multi-class classification. So now you are just guessing, predicting which one of the, the perfect label combination that you're aiming for. So, pretty much this could be 2 different ways to approach multi-label classification, either through a bunch of different binary classification, or doing one single multi-class classification over a bunch of different label combinations.
Is that like a lot?
That's a lot. I mean, so that's how people do it. Yeah, so it doesn't seem like a feasible way, but if you don't have a lot of labels, and if you can get rid of certain labels combination based on heuristics, then it could help. But most of the time people are doing this. Yeah. Cool. We can go over the rest next week. Oh no, Wednesday. Cool. So let's extend the homework 3 to Wednesday to give you more time.